All right, so I want to talk about enthalpy a little bit more. So recall from the previous video, enthalpy it's the change in energy, right? The internal energy of our system under constant pressure conditions. So this is the actual mathematical equation, right? H is enthalpy, it's equal to the internal energy plus pressure times volume. At constant pressure, we can measure the change in our enthalpy using this equation, right? Which is the change in energy plus the pressure, right? Which is constant times the change in volume. So recall from the first law of thermodynamics, right? Our change in energy is equal to the sum of our heat transfer plus the work, right? The heat that is being transferred between our system and surroundings plus the work that is being done on or by our system. So at constant pressure, our heat becomes Q sub P, right? This just means that we have heat transfer under constant pressure conditions. If we substitute this term, right, what energy equals into our equation on the previous slide for enthalpy, we end up with this equation here. And we've also substituted pressure times the change in volume is equal to work. Recall that from our ideal gas law, right? So go back and review that if that is not clear to you, why work is equal to pressure times the change in volume. So when we substitute this energy term into our enthalpy change equation, we end up with this equation here. So our work cancels out and we're left with our enthalpy change is equal to our heat flow at constant pressure. At constant pressure. So enthalpy, the change in enthalpy can tell us whether or not a process is exothermic or endothermic. Exothermic reaction is when the system that we are studying releases heat into the surroundings, right? Which recall from I think it was the last video, when the system releases heat into the surroundings, our Q term is negative because it's losing heat. And so our change in enthalpy is less than zero. So for exothermic reactions, our change in enthalpy is less than zero. An endothermic reaction means that the system is absorbing or receiving heat from the surroundings. And remember, as a result, our heat term, or Q, is positive. So our change in enthalpy, delta H, is greater than zero for an endothermic reaction. So if we want to know if a reaction is endothermic or exothermic, right, we can look at what the change in enthalpy is. We can also look at energy diagrams, right? And energy diagrams, it basically shows the energy change of a reaction. So as we go from reactants to products, we can look at what is happening energetically, right? And then we plot this. We actually plot this. So the reaction progress is just coordinates for the reaction. It could be over time. It could be anything that basically tracks going from reactant to products. And then over this reaction progress, we also plot the potential energy. And from this energy diagram, this gives us a lot of information. But for now, what we'll focus on is it can tell us the change in energy as we progress through the reaction. So here is an example of a reaction where our reactant starts at a lower potential energy, and then once it progresses to products, it actually increases in energy. So this difference, right, this energetic difference between products and reactants is what gives us the change in enthalpy of our reaction, delta H. And in this case, right, if our change in energy is the energy of products minus that of the reactants, our delta H in this case is positive. It is positive. And remember, if our delta H is positive or greater than 0, it is an endothermic reaction. It is an endothermic reaction. And even just looking at this, right, intuitively, you can see that we basically, the reactants needed an energy input to go to products, right? It needed to actually overcome an energetic barrier to go to products. So there was energy that was pumped into the system, which is why it's an endothermic reaction. Now, this is what the energy diagram of an exothermic reaction, right? So here, our reactant starts at a higher energy, and once it progresses to products, it actually decreases in energy. And so the change in enthalpy or delta H is actually less than 0. So it gives off, as this reaction progresses, it gives off heat, and it's an exothermic reaction. The last thing that I want to mention, and actually I want you to pause this video and think about this. You may already know, but if we were to actually touch a reaction, like let's say the reaction's happening in a beaker, if we were to actually touch it, would it be hot or cold for an endothermic or hot or cold for exothermic? So pause this video and think about what it would actually feel. What would the temperature feel like? Welcome back. So in exothermic reaction, right, if it's as the reaction progresses, it's giving off heat. So it's going to be hot to touch. It will be hot to touch. Whereas an endothermic reaction, right, which is receiving energy, will actually be cold to touch. It will be cold to touch. So we can touching the reaction will let us know if it's exothermic or endothermic. I don't know that we'll actually do that we won't use our sense of touch for any of our lab experiments, but I do want you to intuitively or conceptually know, right, if I describe to you a reaction, you should be able to identify, oh, this is endothermic or exothermic, and therefore it will feel hot or cold to touch, right? The other way we will know is we experimentally can measure the change in the internal energy of the system under constant pressure conditions to give us enthalpy, so that value. And we may actually have that value already provided, for example, in a problem, or you may see an energy diagram that traces the energy change of a reaction, and from this you can actually calculate the enthalpy change, and from there determine if a reaction is endothermic or exothermic. All right, see you in the next video.